Hello everyone, myself Dr. Santome Kundu. I welcome you all to this lecture of soft computing techniques. This is the second lecture of module 11. So in the last class we have discussed the rule generation based on Reduct and core. So rough set theory and rule generation. So rough set theory and feature selections. Rough set theory has become a crucial technique for feature selections. It gains importance due to the advancement in data mining and machine learning. Second is that handling uncertainty and incomplete information. So the theory offers a framework for addressing uncertainty, imprecision, and incomplete data. This makes it highly beneficial for real-world applications. That is the rule generations. One of them uses of graph set theory is in rule generation. It's in deriving decision rules that explain relationship between attributes and outcomes. These rules are useful for making informed decision or prediction for new data. Challenge in attribute reductions. Despite its advantages, attribute reduction is a major challenge. Reducing the number of attributes while maintaining accuracy is essential. Efficient computation and preventing overlifting are key concerns. Fourth is a mathematical approach for determining important attributes. A unique mathematical method helps identify the most important attributes. This is done with the help of confidence and strength of an association. Rupset theory in managing complex data for knowledge discovery. First one is that data explosion and challenges. The internet's growth and business need for data-driven decisions have resulted in a massive increase in daily data volume. This data is vast, diverse, and come from sources like social media, e-commerce platform, sensor, and transactional systems. A key challenge faced by organization and individual is how to reduce this data and extract relevant, meaningful information. Role of Rupset theory. Rupset theory offers an efficient tool for knowledge discovery in databases. It helps handle uncertainty, vagueness, and incompleteness in data. It aids in identifying essential patterns and relationships that might be hidden in large datasets. Attribute reductions. Rupset theory supports attribute reduction, which eliminates irrelevant or redundant features. This results in a more streamlined and accurate representations of the data. Advancement in knowledge discovery. Knowledge discovery has been significantly hampered by advancement in next generation databases and management information systems. These technologies have made it easier to store, process, and analyze large data sets. They enable the extraction of valuable insight from complex, high-dimensional data. Importance of data-driven decisions. As business increasingly rely on data-driven decisions, the ability to efficiently mine relevant knowledge becomes crucial. Tools like Rupset theory combined with machine learning and data mining techniques help uncover trends like prediction and support decision making. Sixth is the future relevance of Rupset theory. As the volume and complexity of data continue to grow, methods like Rupset theory will remain vital. They ensure that valuable insights are extracted and applied effectively. Efficient attribute reduction and rule generation method. Goal of the method. The method aims to eliminate redundant attributes. It generates an effective Redux set, which is reduced set of essential attributes that remains core information. Benefits of the reduction process. This process is computationally efficient. It enhances the interpretability of the resulting model. The user can focus on a smaller, more relevant set of attributes, improving the clarity of the analysis. Application across various domains. This method can be applied in several domains, including medical diagnosis, image recognition, financial predictions. In these fields, the feature selection is crucial for improving model performance and reducing complexity. So we know the lower approximation and upper approximation. So suppose we are given an information system that is U and A. So you the set of attributes, you are the set of objects, and this is the information table, which is the set of objects and a set of attributes with decision. So C is called conditional attribute, C is the decision attribute. So in the last class, we also define the upper approximations and lower approximations. So the lower approximation will consist of all the members which surely belongs to the set. And upper approximation consists of all the members which possibly belong to the set. So boundary region is given by the set difference. So these are the boundary region consist of those objects that can neither be ruled or nor ruled out as members of the target set X. You know that if boundary region is empty, these two are equal, then the set is crisp, otherwise it is a rough set. And also the accuracy approximations. So if it is 1, then it is the creep set. If not 1, then it is the rough set. So that things you know. So again, you know the concept of reduct and core. So study one more time. So a reduct represents a sufficient set of condition attributes to identify the decision attributes. It enables the reduction of condition attributes. It contains no unnecessary attributes, making it essential for classifications, help reduce computation cost in rule generations. Finding all possible reducts is an NP hard problem, meaning it's computationally expensive for large datasets. The core is the set of attributes that are essential for classifications and it forms the intersection of all reducts. It represents the minimum necessary features required to preserve the ability to classify or predict outcomes accurately. In a decision table, multiple reducts may exist, and certain rules may appear more frequently in some reducts than in others. There are various methods for finding reduct of decision table. We have learned few. One approach to finding the reduct is through the distributive matrix and distributive functions, which capture the relationship between attributes. The core of the decision table can be determined by identifying all singleton entries in the distributive matrix. A reduct is the minimal subset of attributes that intersects all elements of the distributive matrix, ensuring it remains the necessary information to identify the decision attribute accurately. So you know the decision table. So here we are solving one example. So the rough set theory can be considered as an extension of classical set theory. The basic concept of rough set theory is the notion of approximation space, that is, with every object of the universe we associate some information, that is data and knowledge. Every example of the rough set is organized in the form of information table, which columns are known as condition and decision attributes, and rows of the tables are the object. So here we are considering one table which is that X, Y, Z, W are the conditional attributes and D is the decision attributes, and total objects are 10. So if I write the set of all attributes X, Y, Z, W, so you can try to find the indiscriminity of A. So 1 is different to all others, 2 also different to all others, 3 also different to all others, and 5, 6 different to all others. Only 9 and 10 are the same. Rest all are the difference to all others. So that is indiscriminate relations of A. Similarly, the indiscriminate relations of that is U by D of D is 1, 2, 3, 10, 4, 5, 9, and 6, 7, 8. So if you find the positive region, so let it x1, it is x2, it is x3. So you can find the positive region, you can find the uxy, you can find that the positive region, which is that the union of x belongs to u by d, a lower x, you can find these things. Again you find that ux belongs to u by d and all upper approximation. So if you find all these things, so here is a1 for decision 1, a2 for decision 2, a3 for decision 3. So you can easily find this is the lower approximation. So you can write the positive decision, it is the set of positive decision with respect to the attribute a. You can write here of u by d with respect to a. This is the upper approximation. So boundary region is 9 and 10. So as there is some problem in 9 and 10, as you said, there are this is all values are same, but this is not same. So we ignore that part. So now we initially start with 10 objects. We delete 2 rows because these are the boundary region 9 and 10. So this is the table 2. Now from this table we will generate the rule based on the reduct and core on the table 2. The reduct is the reduced set of relations that conserves the same inductive classification of relations. The set P of attribute is the reduct or covering another set Q of attributes if P is minimal and the intercepted relation defined by P and Q are the same. You know all this the concept. You also know the core is the intersection of all reducts. So by using the disseminated matrix, this uh, we got these reducts XZW, XYW, YZW. So our core is the W. So we cannot eliminate the attribute W because this is the most important attribute of the table 2. By using the confidence or strength alpha, we will find another indispensable attribute of the table. The confidence or strength of an association rule, that is X belongs to D, is the ratio of the number of examples that contains X union D to the another example that contains X. So for table 2, we'll calculate the strength of the attributes X, Y, Z as follows. So now that is for the rules for attribute X. So check the attribute X here. So here X equal to A. So only X equal to A is 3 times and D equal to 1. So X equal to A, X is A and D is 1 and D is 1. So out of the X is 3, D2 is 1, so it is 2 by 3. So rule is 2 by 3. Now X equal to P, D equal to 1. So X equal to P 3 times, so D1 is 1. So X equal to P, D equal to 1 is 33%. Similarly, X equal to P, D equal to 2. The strength of the particular rules come out 33%. Now check here, X equal to S and D3. So X is S and D3. So it is 1 by 1. So the rule is 100% here. The strength there 100%. Similarly, we'll calculate the rules for attribute Y and Z. So for Y, X equal to P, D equal to 1. For Y, X equal to P 2 times D1. So it is 100%. Suppose X equal to P, 3 are there, D is 1. So it is 100%. Now X equal to R. So X equal to RC, this is 4 times. So D is 50%, D3 50%, and that is the 100%. So that is for Y. Now for Z, X equal to 3, D equal to 1. So X equal to Z equal to 3 and D equal to 1. So Z equal to 3 and D equal to 1. So Z3 1, 2, 3, 1, 2, 3, 5 and here 1 only. So it is 1 by 5. Check it on 1, 2, 3, 4, 5. Okay, 1 by 5. So it is 20%. So that is not that. That is 1 by 5, 20%. Similarly, Z equal to 1, D equal to 1. So Z equal to 1, D equal to 1. Z equal to 1, 2, D is also 2. So you can write it is like 100%. So 100%. So Z equal to 3, D equal to 2. Z equal to 3, D equal to 2. It is another 1. So it is 20%. Similarly, you can find all these things. So we get all the string. So this value is better. So we select Y as another indispensable attribute. Indispensable attribute. So now we have the table which is the out of 4 conditional attributes W is core, we select Y. So now in the column we have 4, now it reduced to 2 only. So data is reduced here. So here we have that if a for 1, 2, 3, 4, 8 objects and we eliminate, I mean there is no need for the attributes X and Z. So W is core attribute and Y is selected as another indispensable attributes. Now check the rule here. So for 1, Y is P, A1, here another attribute is 3, P, A. So there is some common attributes are there. Suppose these are the Y, P, A1, this is same, RA2 is same, RP3, RP3 are same. So these are the we need to march these rows. So reduce table 3, eliminating the same values of decision and condition attributes. That is, we can merge different rows that has the same values for condition and decision attributes. This method is called row reductions. We will find that the core of the table 4 in such a manner that the table will remain consistent. So if we eliminate W equal to A, there are two decision values 1 and 2. It means that based on the attribute W, we cannot make a unique decision. Thus, the value of Y cannot be eliminated. Similarly, if we eliminate Y equal to R, there are two decision values 2 and 3. This means that based on the attribute cannot make the unique decision. Thus, the value of W cannot be eliminated. So, table 4 becomes like that. So, what we are going to say here, see here, that P is 1 and W is AS, but still P1 D is 1. Y equal to P, D is 1. Y equal to P, D is 1. Similarly, for here, that W equal to P, D equal to 3. W equal to P, D equal to no role of these things. So we can write like that. So this table, in place of that, we can write star. So now this is the this table is the example. So here we again merge the table. So we can merge the table here. So these two are merged. So we had table 6. We have like that 1 P. So it is Y W D. So P star 1. In table 3 you may write like that. So R A 2, and in column 4 you can merge this thing. So star P3. So this is the basically the table 6. So now further now it is not possible to further reduce the table. So now further reduction is not possible. So table 6 give the decision rules. Following are the decision rules based on the reduct and pour. So here you can write that if y equal to p, then d equal to 1. If y equal to r and w equal to a, then d is 2. If w equal to p, then d equal to 3. So we got 3 rules from the above question. So here initially what we did, we have some decision table. Decision table. First is that we find the boundary region. So with the boundary region, we reduce some objects, reduce some objects. Then with the help of the reduce table and with the help of distributive matrix, we find reducts and core, find reducts and core. Then after finding reducts and core and merging all these things, we got the rules. So these are the concept of the rule generations. So this approach focuses on determining the most important attribute based on the strength of an association. Significance of the approach: it is a promising and new analytical method within rough set theory. The approach can be used for creating new decision rules. Application of the approach: it has wide application field like knowledge discovery, data mining, any field related to attribute reduction and feature selections. Future research could involve testing this method on large databases. This method should also be compared with existing methods to assess its effectiveness. From any decision table, try to find rules or try to generate the rules, find or generate rules. So these are the references of today's class. Basically from this we took the example from this chapter, from this paper. So these are references. Thank you.